The mechanics of deformable bodies is all about two main topics. The idea of stress, how an external force relates to an internal force within a material, and the concept of strain, which is measuring how that external force causes a material to deform. And so if you see this slinky here, if I pull on it, there's going to be stress within the metal, but this object is also going to deform. I pull on it more, it elongates. I push on it, it contracts. And so it's our job to be able to both identify what the stress in a material is. That's going to give us a way of knowing, is this structure going to break? Is the material going to fail under the given load? And we also need to be able to account for the deformation. Maybe the structure won't break, or maybe it'll deform too much to be useful in the engineering environment that we desire it. And so for today's lecture, we're going to talk about strain and the relationship between stress and strain. And so imagine some blob, some general strange object. And we'll take 2 points on this object. Point A and point B. And we can look at the distance between those 2 points. And then we can take this object, and this is in its undeformed state, and we can pull on it, push on it, twist it in a whole bunch of different complicated ways. And we can look at the newly deformed shape, and we want to look at those exact same points. And so we can call them A prime and B prime. And now some deformation occurred that changed the distance between the two of them. So if we call this initial length delta S, and we call this new length delta S prime, we can describe the difference between these two lengths, the change in length, as an average strain. And so we can write that the average strain, given by the Greek symbol epsilon, is going to be delta S prime minus S prime, or delta S. And that looks worse than it is. All we're really saying here is that we want to examine the change in length compared to the original length, or the percent elongation, the percent contraction. How much bigger or smaller did our object get? And that's going to give us an average normal strain. And so we can make this a little bit less approximate, less like an average, and look at the strain as a given point. And the way that we do that is by taking the limit as the distance between A and B goes to 0. And we want to do that along the given axis here, along a given line N. And so you could say that we're going to take the limit as B goes to A along N. And we're going to take the limit of this same equation. And that'll give us the strain at a given point within a material after you've applied a deformation to it. Now this seems hard to work with. A simple way to envision what's going on here is to consider the uniaxial loading of a beam. So here's a beam. It's got an initial length L, and we're going to pull on it by applying some force along this direction. And now we know that this thing's gotten longer in the direction we've pulled it in, so we can call that our new length L prime. We can also recognize the fact that the amount it got longer, we can give that a symbol delta, and we can write that the strain in this case here is just simply L prime minus L over the initial length. So again, you're just comparing the final length to the initial over the initial length. Or, similarly, we know that delta L minus L is going to be equal to little delta. And we can write our strain in this form here, which is a lot more manageable and a lot easier to relate to on a macroscopic scale. So we talked about the change in length as we deformed an object arbitrarily. But we can also look at, instead of looking at 2 points, we can look at 3 points. And so we can put another point here, call it point C. And we can look at the angle between these 2 points. And so if this was a right angle, we'd say that this angle initially started out as pi over 2, and we deformed it in some way. So we got to a new C prime. And now clearly this angle that was initially wide after deformation got smaller, and so we have a pi over 2, and we're going to subtract some angle gamma. That's our new angle. So you could say that our new angle in here would be theta prime, which we'll write is equal to pi over 2 minus gamma. And in a similar way, we can describe this as the shear strain within an object. So how much did the angle between 2 points change as you deform an object? And so a simple way to think about this is to consider a cubic element. So imagine zooming into a really tiny cube within this object here. We have the z-axis, y, and x. And so we'll assign lengths to each of these things such that the length of this element is delta x in this direction, it's delta y here, and it's delta z in the vertical direction. And so first we'll start again with the idea of our normal strain, so the amount this thing is elongating or contracting. And so if we look at a bigger cube, after we've applied some force to it, we can see that the sides of this cube have all gotten longer. And we can write that as, this will be the 1 plus the strain in the y direction times that initial y, right? Because this thing's started with its initial length, 1 times delta y, and then we're elongating it by some strain, epsilon y, and so this new length here gives us the amount that this side has increased. We can do the same at each side here, 1 plus epsilon x times delta x, and again along here, 1 plus epsilon z times delta z. So that's pretty straightforward. All we're doing is saying this thing had an initial length of delta y, and we've applied some deformation to it which caused it to elongate in the y direction by some strain epsilon y. So that's the case for normal strain. And we can additionally look at shear strain, where again we start by imagining a cubic element within this material here. Using the same coordinate system. Instead of looking at the lengths of the sides, what we're going to look at is the angle that the sides of this element makes. And so here we have a right angle, pi over 2. Here, same thing, a right angle of pi over 2. And up here, a right angle of pi over 2 as well. So we start out with this being a cube, with all the right angles at all sides. And then we deform it in some way. And that the deformation causes this thing to kind of resist rotation, change the angle between points here. And so we can write this as our new cube after deformation looks like that. And so now we can go back and look at these angles again. And so what happens here is this side was initially pi over 2, and we're subtracting some shear strain, gamma y z, pi over 2 over here, minus gamma x z, and pi over 2 over here, minus gamma xy. And so again, we're comparing this initial side, which was a 90-degree right angle, and we're deforming it in some way. We've made that angle more acute, and so we're subtracting off that the amount of shear strain that we've applied to the structure. So here are the ideas of strain. Normal strain causing the elongation of sides, and shear strain causing angles within a material to change. So I should make a few notes about strain. First off, as you can see, it's either an angle or it's a ratio between two lengths, which means strain is unitless. It's a dimensionless quantity. Sometimes you might see it written as the ratio of two lengths. So you might see it as inch per inch, or millimeter per millimeter. But just note that this is a dimensionless quantity. The second thing we want to note is that for all the materials that we're going to be dealing with in this course, engineering materials, structural steel, concrete, thermoplastics, all these types of materials, we're going to be concerned with small amounts of strain. And so what that means is we have small strain, so that our strain is usually much less than 0.1. That allows us to simplify some things. Because we have small strains, we can approximate small angles, and so we can say that we can approximate the sine of theta as theta, the cosine of theta as 1, and the tangent of theta as theta. So because we're focused on small strains, we're able to use these approximations throughout this course. So far we've discussed stress and strain. You apply an external force, it generates a stress within the material. And that stress could maybe cause the material to break, or it can cause the material to deform in some way. And so we learned that deformation can be quantified using normal strains, which shows how it changes length, or a shear strain, which shows how points within the material change the angle between them. And so you apply an external force, you generate a stress, you generate a strain. So it should be clear to us that there should be some relationship between stress and strain for given materials. And so how do we determine that relationship? Well, one way is to simply take an object and pull on it. And the idea here is if we can grab an object, pull on it by some displacement, and then measure the force required to do so, we can learn something about the material properties. And so what that looks like, so imagine having some rod of material that's gripped at the ends, and what we want to do is, as we elongate this material, so as we stretch it in the vertical direction by some small amount, delta, we want to measure the force required to elongate it. And so for each amount of elongation, delta, we measure the force. We take that delta and compare it to the initial length of the object. And we take the force that we measure and we compare it to the initial cross-sectional area of the object. So as you can see on the y-axis here we have a stress, on the x-axis here we have a strain. So this is what's referred to as a stress-strain diagram. This is a uniaxial tension test. We pull on the object and we measure what happens. And so a variety of different things can occur. If you take an object that's ductile, say a mild structural steel or aluminum or some thermoplastics, what you'll see is that this thing will rise up and then at some point it'll become nonlinear and eventually breaking. So this is a ductile material. And I'll just explain what's happening here. So at early stages it behaves like a spring. The more you try to elongate it, the more resistance you have, and there's a linear relationship between stress and strain. And then at some point, you can see that it becomes nonlinear. This is what's known as a yield within the material. You can imagine if you take a piece of saran wrap and you pull on it, at some point you pull on it so far that it starts to really relax and become easier to pull on. And this is a yield point here. What you see here is what's known as necking. And so that's when you're pulling on this material and there's almost no resistance to elongating it. The material is flowing in some way. And then eventually there's a hardening and the material breaks. So this is the behavior of a ductile material. The stress strain behavior of a brittle material is much simpler. Brittle material will be linear for some degree, and then eventually it'll just immediately break. A great example of a linear material is taking a piece of chalk. It resists my applied load up until a point, and then it just very rapidly snaps. And then there's fracture and no recoverability. So we have ductile materials. This orange denotes a brittle material. And finally we can have something like rubber, or natural or synthetic rubber, which is going to behave in another nonlinear manner. This is what would be known as a hyperelastic manner, in which it's initially linear, and then there's some hardening until you get to the point where it snaps. And the best way to envision this is to be taking a rubber band, and you can tell if you first grab the rubber band and pull on it, there's some initial stiffness in that rubber, but as you get to the point right before it breaks, you can see that to extend it a little bit further, the rubber becomes much stiffer, and so that's corresponding to this stiffening that we see here as the slope gets higher. So this is fairly complex. We have different types of behaviors for different materials: thermoplastics, mild steel, brittle materials such as this chalk, other ceramics, gray cast iron, and then the behavior of rubbery materials. For this course, what we're really going to focus on is a very, very small region of this stress strain diagram. And if you look down here, you'll see that all of these curves are linear for some region. Now you remember from last lecture we talked about how that we're considering strains that are really, really small. And so if we're looking at strains that are really, really small, we're looking at kind of from here over. And this allows us to focus on our linear relationship between stress and strain. And so what happens is if you look at various materials in this linear region, you see that something like steel will have a stiffness that's on the order of 10 to the 11 if the units on the y-axis are Pascal. Those thermoplastics that we talked about will have a slope of about 10 to the 9. Something like a rubber will be on the order of about 10 to the 6 Pascal. And something like jello or some biological tissues and other hydrogels will be on the order of about 10 to the 5. So you end up going from kind of the tens of gigapascals down to the tens of kilopascals. And this should hopefully make a little bit of sense to you intuitively. Steel, we know, is much stiffer than something like a rubber or jello. And this is basically our measure of quantifying how much more resistance to deformation there is. And so the slopes of these curves are given the symbol capital E, which describes the elastic modulus. And as you can see, there's a linear relationship between stress and strain. It goes through the origin. So you could write this equation as stress is equal to your elastic modulus, also known as Young's elastic modulus, times your strain. And this equation here is known as Hooke's law. And for small enough values of strain, it's valid for all materials. And so we're going to be focused on the limit within this class where Hooke's law is applicable. So we're going to ignore most of what's going on to the right side of this curve and focus on the linear relationship between stress and strain. So since strain is unitless and stress has the units of pascals, the units of this elastic modulus are also in pascals. And here are some typical orders of magnitude that you might see for something. So one thing that we've kind of swept under the rug, if you will, for a lot of these discussions is the fact that in reality, when you pull on an object or push on an object in one dimension, it actually deforms in all dimensions. And so take, for example, this little toy finger trap. If I compress this, we know that it's going to get shorter in this direction, but also watch what happens. As I compress it, it gets shorter in this direction, and in each other direction, it gets longer. And you can see this in action in the other way too. As I pull it, it starts with an initial radius, and that radius gets smaller as I elongate this. And so what we're seeing here can be denoted by a ratio of two strains. So if we have an object that we pull on, in reality, its deformed state is going to look more like this, where we have some strain in the x direction, which is given by the delta in the x direction over L. And so in this case, that strain's positive because it's gotten longer. And our strain in the orthogonal directions, so if we're in Cartesian coordinates, I'd be saying the strain in the y and the strain in the z is going to get smaller by some amount. And so it turns out that what we can describe is a ratio of the lateral strain so in this case the epsilon y to the axial strain. In this case it's epsilon x. And if we can define that the negative of this ratio will be given the Greek symbol nu. And nu is what's described as Poisson's ratio. And so both the things I've introduced today, nu and Young's modulus, these are material properties. So it doesn't matter about the shape of the material. These materials, a given material of wood or rubber will have a particular value of Young's elastic modulus and a particular value of Poisson's ratio. These are material properties that are valid for whatever shape or size of the material you might have. So the elastic modulus, as I've said, usually goes from about 10 to the 5 or about 100 or so kilopascals to about 100 or so gigapascals. Poisson's ratio, typically, if I look at a graph, Poisson's ratio goes from values of -1 to 0.5. Most rubbers have a Poisson's ratio of 0.5. Most engineering materials that you'll deal with in this class and in your future classes typically have a Poisson's ratio between about 0.2 to 0.3. As I said, it can go from -1 to 0.5, although these are very uncommon. In the case of a Poisson's ratio of 0, one example of that is cork. And for examples of Poisson's ratio in the negative values, this is rarely observed but is found to occur within foams and foam-like materials. For this course, I want you to be focusing on a range of Poisson's ratio from this 0.2 to 0.5. This is what we'll see emerge for the materials that we'll be using. So, Hooke's law allows us to relate stress to strain. We can very quickly get an understanding of how to, say, describe the displacement of an object by doing a quick substitution. We take stress, which is equal to force per area. We take strain, which is equal to a deflection or displacement delta over L. And we have that multiplied by Young's elastic modulus. You can very easily see that our displacement, delta, is going to be equal to P L over E A. And we'll come back to this in future lectures, but all we've done here is taken this linear relationship between stress and strain, which we can measure experimentally just by pulling on an object and measuring the force required to displace it a certain amount. We can very quickly go from that to a relationship to predict the displacement based on the applied load, the length of the object, its cross-sectional area, and its material properties.